To talk about the topic which I've been working on during my postdoc at the University of Warwick, and I continue to work on this topic now at the University of Dundee, where I'm a lecturer. So another disclaimer is that it's a collaborative work, so it's not individual work, with a number of colleagues from TU Berlin, from St. Petersburg, and from the University of Warwick. And it's not covered, so the topic will not cover the single specific problem. I would rather make an overview of different problems which we have been solving over the past 6 years and give you the highlights and the main ideas. So I won't show that many equations, but the key thing is just I wanted to show us that what we're working on and sort of what ideas we were developing. So in the title you see that I'm talking about transformation fronts, and the prime example of that is the chemical reaction front. So what's that? So imagine metallic nanowire, so like a germanium nanowire, and if you take that and subject it to lithium, you will see the following picture. So you will see the emergence of two different phases. So you see the light gray phase and the dark gray phase and the interface between them. So this interface is the chemical reaction front, where the chemical reaction between lithium and the pure germanium, which is the core, takes place. And then what you should be able to see, it's a little bit dark, but you should be able to see that the front essentially stopped. And the reason why this front stopped is that it has been blocked by mechanical stresses. So this is the experimental picture, and the purpose of what we are doing, in my opinion, is try to explain these experimental observations. So in this experimental picture, which you have seen on the previous slide, so this emergence of the two-phase structure, the experimentalists plotted the thickness of the lithiated phase as a function of time, like this, and then here you see that it approaches the equilibrium configuration. And we have modeled a similar system, not the wire, but the particle, and we're able to capture this phenomenon of approaching the equilibrium position and mechanical stresses locking the chemical reaction. So it's a slightly different setting and slightly different scaling, but it's just a kind of graphical abstract to show that we are able to capture the experiments. So what do we? What is our general problem formulation? So we talk about the kinetics of the chemical reaction front. So we consider the deformable solid consisting of two phases: the transformed and the chemically transformed and the chemically untransformed phase, and the transformation front between them. So this transformation front is a propagating interface, so it propagates with a certain velocity. And as this transformation front consumes the untransformed phase, the material acquires some intrinsic deformation. And this intrinsic deformation, like chemical expansion, leads to the emergence of the mechanical stresses. So this kind of picture can describe different physics. So we can describe stress-induced phase transitions, or if we also add a diffusive reactant which diffuses through the transformed phase and participates in the chemical reaction front, we can describe chemomechanics. And the key physical question is that what's the influence of stresses in this case? I need to introduce a couple of things. So from the classical chemical thermodynamics, I'm sure that like most of you know these things, but for those who don't know, I will just introduce them on this specific slide. So remember reactions in the volume. I guess that's university undergrad stuff. So if we have a reaction between gases in the volume, like methane or oxygen, and oxygen, by definition of stoichiometry, we have the proportionality between consumed masses of these reactants and produced masses of these reactants, and the molar masses and the stoichiometric coefficients. So this ratio is the kind of the reaction extent, or the reaction coordinate, sometimes it's called in literature. And the time derivative of this reaction extent is called reaction rate. So reaction rate is essentially like amount of mass of different reactants consumed. normalized by the stoichiometry, the corresponding stoichiometry and the molar masses. So then in case of mechanical thermal equilibrium, the only changing thing in our system thermodynamically is this reaction coordinate, this reaction extent. So it means that the amount of entropy produced, which is temperature change in entropy minus the heat supplied to the system, would be proportionate to this infinitesimal change of this reaction extent. And this proportionality coefficient A in front of it is called chemical affinity. And it's a function of state variables. So thus, in the classical thermodynamics, so the two things I introduced, the reaction rate and the chemical affinity. And they are typically linked by constitutive law. So we link the kinetic quantities and the thermodynamic driving force. So this chemical affinity is a thermodynamic driving force. Right? So this is like the undergrad stuff about thermodynamics. And then now we consider the reaction rate-oriented surface. So going back to this visualized slide of this germanium nanowire, or lithiation of silicon. So we actually worked on lithiation of silicon in lithium-ion batteries. So this reaction takes place on this oriented surface, gamma. And then in this case, we have exactly the same behavior. So we have so exactly the same entropy production. But now this proportionality coefficient, so this chemical affinity, becomes the normal component of a tensor. And this tensor, so this bold A, it's logical to call this tensor a chemical affinity tensor. But it's also, it's one more remark, this chemical reaction rate, in this case, is not the chemical reaction in the volume. So the masses are not consumed in the volume, the masses are consumed at the surface. So this chemical reaction rate must be related to the interface velocity via the mass conservation law. So this tensor is a chemical affinity tensor. So don't look at the equations now, it doesn't really matter. So the key thing is that we can derive this tensor from thermodynamics. So when we consider this entropy production on propagating interface, we can derive the expression for the thermodynamic driving force for this tensor. So the actual expression for it doesn't really matter. And then we relate this driving force to the kinetic quantity to our reaction rate. And thus we can get the velocity of this interface. So right, this is the theory. So then we obviously have mechanics, we have diffusion, so I'm not showing that. So first thing which we have modeled was lithiation of silicon nanoparticles in anodes and lithium-ion batteries. So the problem with silicon is that it undergoes huge volumetric expansion when it's subjected to lithium, and this produces enormous stresses, and the stresses block the chemical reaction. So, and then obviously we don't want to have chemical reaction block because we want our battery to undergo full 100% lithiation. So we model particles with elastic core because the core doesn't have divertoric stresses applied to it, and elastoviscoplastic shell in large deformations. So the constitutive law looks something like this. So we have stress-strain behavior. So with strain rate dependent yield stress. So it's like elastoviscoplastic material. And so one of the highlights of this work was that we can get the front velocity as a function of the front position. So initially we have pure silicon, then the front propagates, and then in the end we have fully lithiated silicon. And then the front velocity initially grows, then we have a plateau, and then it severely drops due to the buildup of stresses. So, and then we have obviously two energies in the system. So we have mechanical energy and chemical energy, and they compete between each other. So if we change the chemical energy, we can have different pictures. So with extremely low chemical energies, so the front velocity is close to zero in the beginning. It means that for super low chemical energies, the reaction won't even start, because the mechanical stresses won't allow that. So it also relates to what we see in reality. So in the low temperatures, we can't really start reactions, so because the chemical energy is too low. And then we can see that the locking stress also is, so the locking state is moving further as we increase the chemical energy in the system. So we then looked at a model where we embed the particles in the matrix. So we did this in a mean field way. So we performed mean field homogenization. So we used the Mori-Tanaka scheme to sort of surround particles with a viscoplastic matrix. So this is the picture we have seen before, the isolated particles. But now, so when we increase the matrix stiffness, so when we sort of surround particles by the matrix, so you see that the front velocity drops, which is logical, right? So the matrix applies stresses, so the higher stresses, they block the chemical reaction earlier. But then there is another interesting thing you see here. There is a kink in the velocity profile, and this kink is related to the onset of plasticity in the matrix. So we actually have the effects of the matrix on the reaction kinetics directly. So, and then if we consider an extreme case, we take the very stiff matrix, but we add viscoelasticity to that. So then we will have the interesting effects. So we'll have a relaxation time of the matrix, and we have a typical characteristic time of the chemical reaction. And then again, they will be competing. So we can see interesting picture. So in this case, the front velocity can go with this sort of decelerating, accelerating, and then decelerating pattern. So in the first reaction wants to lock itself, so because the stiff matrix doesn't allow the particles to expand, so the stresses build up. Then stresses relax, so we have acceleration of the reaction because stresses in the matrix relax. And then so when they relax, we still have a buildup of stresses within the particle, and then the reaction locks. So it's kind of intuitive, but it's good to obtain these results computationally as well. So I have showed you that the chemical reaction flux and approaches this interfaces, they approach equilibrium. But you know that equilibriums can be stable or unstable. So then it means that under some conditions, we might have an interface which is unstable. So then we investigated that. I had a slide with equations here. I think I'll just quickly run through them because they're fairly obvious. So for mechanics, so we have linear momentum. So so stability wins. So before this, the previous results were under large deformations. For stability, we looked at small deformations because it makes sense to investigate the stability. So we perform linear stability analysis. So it makes sense to consider for that linear elasticity and small strains, obviously. So so we have linear momentum balance. So we have Hooke's law. So we have transformation strain, intrinsic transformation strain in each phase. So diffusion described as a stationary diffusion process. Stationary diffusion. We have interface conditions. So we have continuity of displacements, continuity of tractions. And for the diffusion, we have the flux at the interface, which is consumed by the reaction rate. So this omega, the symbol stands for the reaction rate. And then we have reaction kinetics. So again, don't look at the equations. So the important thing is that we have them. So I'm just using them as a picture. So we have them. So we have the kinetics of the reaction, which was, so the NN is this chemical affinity, which was derived from thermodynamics. And a relation between omega and the NN is the constitutive law, of which we kind of generalized from the what we see for the gases. And then we have the velocity of the front, which is related to the reaction rate due to mass conservation, due to mass balance. So, so the idea behind linear stability analysis is that, so we have something which is unperturbed, so the unperturbed interface. So we apply perturbation and then see whether this perturbation grows or decays. So we have, so the position of the front, so we apply the perturbation to the position of the front. And this necessarily leads to perturbation in the solutions. So U are displacements. So perturbation of the solution and the perturbation in the concentration. So, so we have these two perturbations, so we need to find them first. So we get the linearized boundary value problem with respect to these perturbations. But these boundary value problems are defined on the perturbed geometry, which is actually quite difficult to solve. So the first step within this is to rewrite the equations onto on the unperturbed geometry. So you project everything on the unperturbed geometry. So you project the interface conditions. So for mechanics, this has been done in 2000s, and for diffusion, which has been done by my co-author within his PhD thesis. And then we find, by solving these boundary value problems, we find these perturbations of the displacements and concentration as a function of the perturbation of the interface, and then we get the linearized kinetic equation for the interface. And then, as I mentioned, the physically stable or unstable behaviors, they will correspond to the decay or growth of this perturbation of the interface. So we played around with this concept, and our main result is that we consider the planar interface, and for the planar interface we have a mathematical proof that diffusion doesn't affect stability. So stability is purely defined by what's happening on the mechanical side, so by in this case the elastic moduli and the mechanical loading. So for my course also looked at that for the cylindrical geometries. So for that we couldn't obtain the mathematical proof, but we have numerical results which also coincide with that the diffusion doesn't affect the stability. I'll skip that. So next element in our ability to be able to investigate this problem is obviously sort of the set of computational tools which will allow us to do more complex problems, not only something which is spherically symmetric or planar. So in terms of computational methods, we're dealing with the interface, and there are different ways how to deal with the interface. So if we stay within the concept of sharp interface methods, which are also finite element based, we essentially have only 3 options. So the first option would be doing something like remeshing. So we have interface, and then as the interface moves, we create completely different finite element mesh. So the second option would be mesh distortion. So you don't change the mesh, you just change position of the nodes, but you don't change the topology of the mesh. So the problem is that then you'll create a highly stretched and elongated finite elements, which is kind of fine within is a geometric setting, but it's not fine if we have the kind of standard finite elements. And the last option, which is most appealing to me, is when we have the background mesh and the interface which cuts through the elements. So in this case, the interface can move independently of the mesh. So it's kind of like if you are familiar with the XFAM strategy, so it's kind of similar idea with the XFAM, but what we specifically use is the CutFAM method. So we spent quite a lot of effort in sort of working on this, but I will just show the kind of the basic idea. So the CutFAM is a fictitious domain method, which means that we have a finite element mesh which is kind of spreading to outside of the geometry of our body. So here I'm just drawing the boundary of the body, but also we handle the interface exactly the same as the external boundary. So there is no difference in that. So the CutFAM method is characterized by weak enforcement of the boundary conditions using Nietzsche method, and by inter-element stabilization, which is enforced on the internal boundaries of the elements, which are cut by the interface. And originally it has been formulated for linear PDEs, including linear elasticity, so that has been done before us. Oh, so yeah, I need to mention, probably I should have mentioned that first, that there are other non-conforming mesh methods. So a lot of people worked on GFAM, XFAM, there is enhanced gradient FAM. It's really cool new method, which is shifted boundary method. I really like it, but didn't have much time to look into that. So there are other methods, but we work on CutFAM. So CutFAM has been done for linear problems, and we specifically work on CutFAM for large deformations in solid mechanics. So we have generalized it for large deformations, so which are non-linear problems, and we did it in several steps. So first we did it for phase boundaries and these chemical reaction fronts. Then we actually did fracture and contact, which is completely outside of the scope of this presentation, but we also did that. So just one slide, I'm not showing you the method. So that is covered in these 2 publications, just to show that it works. So imagine a stationary interface within, like, let's say, a square domain stationary interface that cuts through the elements. So the bottom phase undergoes 10% transformation strain, so it expands. It means, well, why it expands? It will bend the top phase. And then we can do that using cut elements, and we can do that using the standard finite elements. So we get the second order conversions. So this shows us that not only method works, but also my implementation in MATLAB is also working correctly. And then we've done many more tests. So I'm just showing you the one to show that the method works. So then we use this method to look at the stability of these interfaces computationally, and to solve also other problems. But I'm covering the stability in this, this next couple of slides. So, oh, 2 minutes. Okay, right. So, what should I? Okay, I'll skip all that. So just some kind of one new thing which we have been working on recently. So I showed you the interfaces. So I showed you the chemical reactions which are taking place at an interface. But there is also experimental evidence that the chemical reactions can smear out. And these reactions can take over kind of a range of, so over basically over the volume. So the chemical reaction will be between the gas and the solid, but it will take place in the volume. So this is, these are experimental results of lithiation of silicon particle, not ours, of course. So during the first lithiation, you see the interface. So you see this, if you look closely, so there's a dark gray and a light gray phase, and then this is the interface. This is the setting which we have been covering up to now. So, but then during delithiation, you don't really see the interface. And during the second subsequent lithiations, you don't see the interface. So this is the indication that the reaction takes place in the volume. So the schematic, this author of this paper schematically shows this, that during the first lithiation, we actually have the interface. But then during cycling, we have the reaction which is taking place in the volume. So it means that we also want to have the theory which will also cover that, which will cover reactions taking place in the volume. And we have been working on that. So the key thing in here is that now the diffusion, so first of all, it becomes non-stationary. So the second thing, it will have the reaction inside the diffusion. So the reaction will be inside the diffusion equation taking place in the volume rather than on the interface. And then you also have sort of energy balance, and then you also have mechanics. And then the dissipation will still have the same form. It will have the chemical affinity times the reaction rate. And then you can derive all you can derive all the quantities, and then like Poluektov stresses, the chemical potentials, which will have stresses on them, and the chemical affinity. So you can derive these expressions from thermodynamics. So this is what we did in our recent publication. And then you can do several things. So here, so one option is that if your Helmholtz energy density, if your Helmholtz free energy per unit of volume in the reference configuration depends only on the reaction extent, you will get something like a volumetric reaction. You will get a reaction which will be smeared down in space. So, but you can also do other thing. You can do a few tricks here. So with the kinematics and with the stresses, you can kind of split kinematics and stresses using the gradient of this reaction extent, and plug in also this gradient of the reaction extent into the free energy, and then you can have something like a phase field method. So you can actually create a phase field method from this theory of volumetric reactions. So this is our recent work, which is not published yet, so which is under preparation. So to be able to do this phase field properly, several tricks are needed. So first of all, you need to handle kinematics. So you need to introduce, so within the volume, you just only have one deformation gradient. So you need to introduce the deformation gradient of the transformed phase and the untransformed phase, although you don't really have them. So you kind of imagine that you have them like this, there's F plus and F minus. And the phase field people came up with that for the phase transitions before us. But then sort of the chemistry part is what we have done recently. And then you handle the Poluektov stresses in the same way. So you split them into transformed and untransformed Poluektov stresses in a certain way. And within this free energy, as I said, so you use something like a double well potential for phi, and the standard sort of gradient term squared for the gradient, and then you get the phase field stuff. And then we can actually get the localized reaction from that. So first thing is that our main result was that the chemical affinity, in this case, will have the same structure as the sharp interface theory. So in limit, in our phase field description, we can get the sharp interface theory, and we have proved that. We haven't published that yet, though. And So we model the reaction locking again. So going back to this reaction locking case. So we model that in 1D, just as a demonstrative example. So we start with an interface, and then you see this interface actually stays as an interface and propagates and locks at a certain point. And obviously, for the volumetric reactions, you also have the concentration, which can be defined within the volume. And you see this the kink, which is exactly the position of the interface, but you see that the concentration actually spreads beyond the interface. And then as the reaction locks, we still have diffusion into the untransformed phase. So we still have diffusion in the untransformed phase, but we don't have the reaction there. So just to conclude, so the transformation fronts are encountered in industrially relevant problems, and mechanical stresses can block these transformation fronts. These transformation fronts can be stable or unstable, and we have been able to sort of model the stability both analytically and numerically. Numerically, I haven't showed this. Yes, but sort of we have some publications. Well, we have one publication on that. And numerically, we can do that with cut element technique, which we developed specifically for modeling the kinetics of the interfaces. It has advantages over its competitors. Some advantages, but I'm not going to discuss that further. And our recent work was that we also modeled these reactions using kind of phase field type method, which converges to the sharp interface approach in the limit. So we can do both phase field description and the sharp interface description. Okay, thank you very much.